Okay, so what I'm about to show you is a visual for what I was just describing. Essentially this, except in the visual, delta x is going to be 2, just like with the table over there. Here's a static diagram where delta x is 2. So here's x right there. It's 2 as well. Then I'm increasing x by 2. This is really a 4. X plus 2 would be 4 here. I'm looking at the outputs of this exponential function, and this is what the graph of a typical exponential growth function looks like. That's the kind of picture that you're going to typically see. The output of 2 is about 4.5. The output of 4 is about a little bit bigger than 10. The input got multiplied by 2. Notice the b is 1.5 here with this example. B is 1.5, and delta x is 2. This is going to be 1.5 squared. You're going to multiply the output when x is 2 by 1.5 squared to get the new output when delta x is 2. 2 plus 2 is 4. Right? That's what happens. This is a 1.5 squared factoring. It's not a distance there. It's a multiplication. That's a little confusing. I probably should have used some other way to represent this. 1.5 squared is not the distance. 1.5 squared is 2.25. Definitely not the distance. It's what to multiply f of x by to get that. That number, a little bit bigger than 10, is about 2.25. Is 2.25 times bigger than the second coordinate there. Try with the calculator. 4.5 times 2.25 is 10.125. A little bit bigger than 10. Okay? It doesn't matter what x is here. Here's the animation. X can be anything. Delta x is still 2. I am increasing the input by 2 plus 2. The output gets multiplied again by 1.5 squared. B to the delta x. Okay? This is what an exponential growth function looks like when b is bigger than 1. This is what the graph looks like. When b is between 0 and 1, that's called an exponential decay, and the graph looks like this. But in either case, the a, which is 2 in this case, is the initial value. It's the value of the y-intercept. It's the output of the function when the input is 0. Okay? Can I clarify anything about that? Mm-hmm.
What's the value that's changing?
X is changing. So the blue dots are moving. This blue dot is moving, which causes everything else to move. Right? This blue dot is the value of x you see up there. That's x plus 2. That moves as well as the outputs move. More about exponential functions. Okay, this gets more complicated. Okay, we have to deal with some complicated things. They are often written in alternative ways. Here's the first way we already talked about. Here's a second one. And I purposely put a t for the independent variable. For one thing, just to realize, again, the letter doesn't matter. And for a second thing, most commonly, applications of exponential functions, the independent variable is time. And so it's most natural to use a t. That's actually a more natural thing, typically, to use for the input of an exponential function. Most typically, it's time. I'm emphasizing that a is the initial value here as well because I'm using a y sub 0. Y sub 0 is a notation commonly used for the initial value of a function, the output when the input is 0. It's a constant. This whole thing, y, that's a subscript there. Y sub 0 is just one number. The 0 is just a label. Right? Other labels like y1 or y2 as well. This is y0 times 1 plus r to the t. So I'm treating the b like a 1 plus r. So if b must be positive, r must be bigger than negative 1. And if b is not equal to 1, r must be non-zero. While b is called the growth/decay factor, r is called the growth rate. Maybe call it the decay rate, but I think it's better in the case when r is negative to say that the growth rate is negative and the absolute value of r is called the decay rate. So, for example, if r is like negative 0.2, then 1 plus r is going to be positive 0.8. That's going to be the same as b. You'd say the growth factor in that case, slash decay factor, is 80%, which means that as x increases by 1, the output changes by 80%, which means it goes down, it decays. Like 80% of 100 is 80. 80% of 80 is 64, right? Yeah. The output as x goes up would keep going down when r is negative and b is between 0 and 1. It's going down by 20%. R itself is negative. You could say the growth rate is negative, but the absolute value of R would be positive 0.2 or positive 20%. You could also say the decay rate is positive, it's 20%. The word decay then would mean it goes down in value. These are technicalities that are easy to get confused by, so you want to make sure you're, again, paying attention to details. There's yet another way to write these exponential functions. That's going to be the most common way for us in calculus. And there's a good reason for it, which we will see later. Using the number e. E is a special number like pi that has a decimal expansion that goes on forever and ever without a repeating pattern. It starts 2.718281828, which makes you start thinking it's repeating, but it actually does not. And it goes 459. E is irrational, just like pi. You know, people try to memorize pi to thousands of digits. E feels so neglected. You guys should start an E memorizing contest. Okay? E is just as important as pi, if not, in some people's opinion, more important. I'm not going to say one is definitely more important than the other. And k is non-zero. Notice that the exponent of the E is not just a t, it's a k times t. K is called the continuous growth rate. I'm not going to explain what that means at the moment. Okay? I think I'll leave that for next Monday. We've got enough to do today. Just like with R, if k is negative, then the continuous growth rate is actually negative, meaning the function is actually going down, it's actually decaying. And you'd say its absolute value is the continuous decay rate. You put the word decay. Again, it's a little confusing. It might have been best to just call this a growth factor and not put the slash decay in there. So I'm kind of being a little inconsistent here with the language. Some important relationships are these. All these equations are true and equivalent to each other. B equals 1 plus R, and also equals e to the k, without a t, right? Essentially, the t is 1 then. Solve that for r is b minus 1, it's also e to the k minus 1. Solve for k, and you get the natural logarithm involved, ln. Now, we are officially not doing logarithms in our textbook until section 1.4 or 1.5, I think. But really, you know, that's something you should have learned in the past. It's essentially just solving this equation for k by taking the natural log of both sides, or of all three quote-unquote sides. Okay, this will make more sense when we do talk about logarithms. But these things are worth knowing. We're not done here. There is yet more complication. And again, this may feel overwhelming, but it's all pretty important. And it'll all make more sense if you think about examples as you work through the completion and graded assignment over the weekend. I think it should make more sense when you put enough time into it. Okay? You got to put the time into it. Yet more about exponential functions. Here at a doubling time or half-life. Okay, those are common applications of exponential functions, like with population growth or growth of money in a bank account or radioactive decay. Exponential growth functions have constant doubling times and also constant tripling times and quadrupling times and quintupling times, hextupling times, septupling times for 7, octupling times. The amount of time in any given situation it takes to double is constant, no matter the starting amount, no matter the amount or value starting amount. Exponential decay functions have constant half-lives, or third lives, or fourth lives, or fifth lives, etc. An amount of time for the amount, for example, of a radioactive isotope to decay to half of what it started with. Common example is carbon-14. It decays to what, carbon-13 or carbon-12? I don't even know for sure. Probably carbon-12, that's more common, right? Like carbon-13. And so it loses some neutrons over time. And after a certain number of, I think it's 5,000 something years, it's half as much that was there at the beginning of the carbon-14 isotope. It's a half-life. You can find formulas for the doubling time and half-life. If T2 is the doubling time of an exponential growth function, here's the line that tells you how to find T2 in terms of what K is. So again, we're using the E form of the exponential function here. That is going to be the most common form because it is actually most helpful for calculus, to use E. What am I doing here? I'm saying, okay, I want the doubling time, the function value at the doubling time to be twice what I started with. You should be able to take these symbols and think about what they mean. This is the value of the exponential growth function at the doubling time. Actually, it's growth. Think of this as money growing. How long do you need to leave your money in the bank for it to double in value, for example? I want twice the starting amount. F of 0 is the starting amount. Plugging in 0 into the formula, I get e to the 0, which is 1, so it simplifies this. I'm trying to solve this equals this for T2. The y0's canceled. The initial amount is irrelevant. The y0's canceled. Divide both sides by y0. You get this equation if you do that. Solve for T2 by taking the natural log of both sides. Initially, you get kt2 equals the natural log of 2. And then just divide both sides by k. You might have seen this formula before. That's the formula for the doubling time. And if you know the doubling time, then it's really, in some ways, more convenient to write the exponential function like this. And this should make good intuitive sense, because if you replace little t by t2, right there, you get t2 divided by t2, that's 1. 2 to the first is 2. y0 times 2. y0 has doubled in value. Analogously, if t sub 1/2 is the half-life, then you can do similar kinds of calculations. So half-life, again, is when some substance, for example, is going down like carbon-14 to something else. So the amount of carbon-14 is going down. How long does that take to happen? I'm calling that T1/2. Really, K is negative here. If this is going to be exponential decay, K is really going to be negative. I say that at the end there. F of T1/2 is going to be half of what I start with. My goal, I simplify, my goal is to solve this equals this for T1/2. Once again, cancel the y0s, use a logarithm. There's a property of logs that says the natural log of 1/2 is the negative of the natural log of 2. We'll talk about that more when we talk about logarithms. This is still a positive quantity here, though, because K itself is negative. So these doubling time or half-lives, these things are positive numbers, even when you see a negative sign. And once again, the exponential growth decay function in this case, it's more natural in some ways to write it like this, because again, if you replace little t with T1/2, this becomes a 1. 1/2 to the first power is 1/2. We get 1/2 of what we started with when we replace little t by the half-life. And this can also be written with a negative exponent instead. This is maybe a more common way to write it, because of the property of exponents. So again, this is it's abstract. That makes it difficult. But it's so worthwhile to just keep working at trying to follow this. And I would recommend looking at these in your notes, writing it down, or these slides, incoming days as you study for next Wednesday's quiz, for example. Okay. Getting close to the end here. I also want to use, at the end of class today, Mathematica a little bit, to show you a little bit about how you use Mathematica. You've got a completion problem where you use technology. You could use your calculator, and that's fine if you do, but I also do want to show you how to use Mathematica a little bit, because you will be using Mathematica for your projects in this class. Okay, so we want to start learning how to use it a little bit. Remember I talked about calculus-related properties of linear functions last time? We can talk about calculus-related properties of exponential functions. Actually, again, the last one's not really calculus, but I'm putting it there anyway. Just like linear functions, exponential functions are continuous. You can draw their graphs without picking up your writing utensil. That's not an official definition of continuity, by the way. It's just a nice visual description. Here's an exponential growth function. I can draw it without picking up your writing utensil. Here's an exponential decay function. I can draw it without picking up your writing utensil. Although that's a little bit of a lie, because really the graph goes on forever and ever, so I didn't really draw the whole graph, yet I picked up my writing utensil. Okay. You have to imagine that you can draw the graph forever and ever. So continuous, no breaks in it, no holes. That's actually difficult to prove. General, okay? Takes some pretty advanced math to prove that. At least if you're starting from simple principles. They're smooth, just like linear functions. They got no corners and no infinite slopes. Nice, smooth graphs, changing smoothly. The derivative will exist everywhere. The slope of that graph can be defined everywhere. It's the slope of something called a codomain. You have, like I mentioned already, a constant relative rate of change. Constant percent rate of change, including instantaneously at any point. Not just as delta x is some fixed positive number, but also at any point. That's kind of a subtle thing too, that we'll talk about that more later. What are the domains and ranges? We haven't talked about domains and ranges yet. It was in the reading from section 1.1. So these both exponential growth and decay have the same domain and range. What's the domain? All real numbers, the set of all real numbers. You can plug in any real number into these functions. You can graph it above any point along the horizontal axis. For both cases, the domain is the set of all real numbers. Now, I'm okay if you write it like this. I am using, I guess I'd be even okay if you don't use the curly braces here, but if you want to emphasize it's a set, a collection, you really should. There are shorthand expressions for these things, this thing. Sometimes you'll see this. The interval from minus infinity to infinity, even though infinity is not a number. There's not a point, by the way, it's an interval. It looks like a point notation. I prefer actually a fancy looking R, double struck R, looks like that. That represents the set of real numbers. I just like fancy symbols. Okay? So that's the domain. You can plug in any real number. What is a range in general? The set of all possible outputs. I actually don't like the word range, though it is the word our book uses. I prefer the word image because there is a situation, this was more common in the past, when the word range had a couple different meanings. Some people took it to be the set of all outputs. Some people took it to be the kind of outputs you get. not the set of all possible outputs, which are different things. So in this case, well, what is it in this case? What's the set of all possible outputs? All numbers greater than 0. You can think of it as being numbers that are possible y-coordinates on the graph. Everything strictly above 0. 0 is not a possible output, even though it gets really close to 0. You could write this in various ways. You could say the set of all y such that y is positive. I'm using y because that's the typical output letter. This vertical line means such that, or with the property that. Set of all numbers y such that y is positive. You could also use interval notation like that. Those are the two most common ways to write it. If you just wrote y is greater than 0, would I mark it wrong? Probably not. I'd probably say it's fine. But if we want to be technical about it, to emphasize it's a set, write it one of these ways. So that's what our book means by range, set of all possible outputs. But other books say the range is just the kind of outputs you get, meaning any real number. But we don't get negative outputs here. We also don't get 0. Well, okay, I should say A is positive in both these cases. You can get negative outputs if A is negative. A times B to the x would be negative in output if A itself is negative. We don't take B to be negative. That would be bad news. Right? Don't do that. For the kind of outputs, I would prefer the word codomain. Though that's not a real common word here. It is in some books, though. Are exponential functions one-to-one? Are they onto? Here's where the distinction between range and codomain is important with the onto question. What does one-to-one mean? That's what all functions have. He said every input has exactly one output. That's true for any function, including non-one-to-one functions, but it's similar. I'm glad you tried it. It's a similar kind of idea. Instead of every input, every output has at most one input that has that output, or goes to that output. Or weird to say. Is this one-to-one? The possible outputs are the numbers on the vertical axis above the origin, where y is positive. For every one of those possible outputs, there is exactly one input, because the graph passes the horizontal line test. No horizontal line goes through the graph more than once. You need to pass the vertical line test to be a function, to be the graph of a function. You need to pass the horizontal line test to be a one-to-one function if you assume it's already a function. Again, what's special about one-to-one functions? They have, anybody know the word I'm looking for? It starts with an I. No. I'm glad you tried though.
Inverse?
Inverses, yeah. F inverse exists, at least if you choose the domain for F inverse appropriately. Are they onto? Well, it depends on what you mean. What we typically mean is we're saying, are all real numbers possible outputs? And the answer is no. But if we restrict the codomain to being just all positive numbers, then the answer is yes. So the onto question can be changed from yes to no just by changing whatever you're considering the codomain to be. What are the limiting values? Let's just focus on the exponential growth one. This function here, what do you think I should write that this equals? Well, let me write it as a times b complete x. B is bigger than 1. and a is positive.
Infinity?
Infinity. When I write that, I'm not saying infinity is a number. And because of that, maybe it'd be better to put quotes around the equal signs, but okay, we'll leave it like that. All I'm saying is I can make this function go above any possible horizontal line, no matter how high, by making x big enough. Which makes sense when you think about the graph. It looks like it's going to be that way. And what about as x goes to minus infinity, as x goes to the left forever and ever? Zero. The graph is getting closer and closer to zero. To be a bit more precise, it's getting arbitrarily close to zero. I can make it as close to zero as I want by making x big enough to the left, big enough negatively. These are subtle concepts, okay? You gotta continually think about them. Let's use Mathematica now. Get some basic practice with Mathematica, and that probably will be the end of class. Oh, okay. Oh, sorry. I showed this entire page all at once. I meant to animate it. Let's go ahead and look at number 4, okay? You should try 1 through 3 on your own. So we're going to try to solve the equation 5e to the 3t equals 17. I shouldn't put it there. 5. That is 17, right? Yeah, okay. Introduction to Mathematica.
What would be the limit if it was taken?
So then it would be 0 as x goes to plus infinity, and infinity as x goes to minus infinity, because the graph goes like that.
It would be like opposite infinity.
The output doesn't go to minus infinity if a is positive. Okay, Mathematica can do lots of really fancy things. Certainly it can do basic things like, well, what's 1 plus 3? 4. How do I get that to do that? I type 1 plus 3, and then I get, here's something to write down. On shorter keyboards, which most of you have, you have to do shift return when the cursor is on that line. To get the output, do shift return. You should write that down. Shift return to get the output. So certainly it can do real basic things, but we're almost done here, so we need to do something more complicated. We want to solve that equation here. 5e to the 3t equals 17. Mathematica is built from what are called Mathematica functions, one of which is solve, capital S, then lowercase o-l-v-e. Mathematica functions, commands, start with capital letters always. That's what's right here. The input for those functions goes inside square brackets. So I put some square brackets there, and I'm going to type some more inside there as well. These are functions. They have inputs and they give you outputs. The inputs are going to be expressions. The output for solve will be hopefully a number. If I want to solve this equation, I go ahead and type the equation. But how do I get the number e in there? The quickest way is with a capital E. A lowercase e is no good. Capital E in Mathematica represents the number e. That's worth writing down. I want to set this equal to 17 and solve for t. Here's something else very important. You got to put 2 equal signs, not 1. When you're solving equations in Mathematica. If you put 1 equal sign, it'll get it messed up. And it makes you all frustrated. Okay? 1 equal sign is reserved for other things, which I'll talk about later. Solving equations, you use double equal signs. Then you put a comma and the variable you're trying to solve for, t. Now when you solve this equation, try to imagine solving it on your own. Divide both sides by 5, then take the natural log of both sides. The answer is going to involve natural log, ln. On Mathematica, the answer will also involve the natural log. However, Mathematica calls it log, which gets confusing and makes other weird things here too. Why do that?
Did you mean 17?
Yes, thank you, 7. Well, it's still weird. Okay, I don't know why it's doing this weird thing. It's making it more complicated than it needs to be. It doesn't usually do that. I don't know why it did.
That's what mine did as well.
Okay. So I should have tried this ahead of time. Okay, that sort of worked. It's using log with a capital L here for the answer. But this is actually natural log. Why are they doing that? Just to confuse us? No. It's because mathematicians and physicists hold the natural logarithm, log base e, in such high regard that they say that's really what should just be called log. That's the true logarithm. They're not trying to trick you, it's more of their bias. They prefer that from the natural logarithm when you get to real high mathematics, graduate level math. Okay? So that actually means natural log of 17 times 1/3. You should check that on your own. Have a good weekend.